So silicon carbide today is no longer a new technology. Actually, ROHM has developed silicon carbide devices for over 20 years, and we have established a vertically integrated production system from substrate level to wafer devices and packaging. So on this slide, you can see we were the world's first manufacturer of some silicon carbide products, the MOSFETs, trench type MOSFET, and packaged products. And we have our wafer, substrate wafer coming from wholly owned subsidiary SiC based in Nuremberg, Germany. And we have multiple fab locations to make devices in Japan. And we have packaging facilities in our Kyoto headquarters as well as other Asian countries to make discrete and power modules. Silicon carbide market, global market is growing rapidly and is primarily driven by the vehicle electrification market. You can see the automotive inverters and onboard chargers and also industrial applications really increase the silicon carbide market volume to multiple billion dollars. And in this market, ROHM is one of the technology leaders. As you can see, we have produced silicon carbide MOSFET as early as 2010, and since 2021, we announced the Gen 4 trench type silicon carbide MOSFET technology, and now we are expanding the lineup of Gen 4 products. ROHM has partnered with many customers, including automotive tier one suppliers, OEMs, to make our silicon carbide MOSFET useful and good for the EV market. So most recently, we have signed long-term supply partnership with Vitesco with over $1 billion of supply relationship, and other partners you can see based in Japan, China. Basically, we have supported many leading customers to develop their high efficiency traction inverter and onboard charger solutions. Silicon carbide, in the silicon carbide production chain, the substrate level is actually quite important because it is difficult to master the know-hows to make high quality silicon carbide substrate materials. It's not as established as silicon substrates. ROHM, for this reason, we have made internal investment in substrate material. We wholly own SiC in Nuremberg, Germany, and our company has been the top three market shareholder for silicon carbide substrate. So we supply our own device manufacturing from SiC, and we also support other device manufacturers and supply substrate under long-term agreements. To support the rapidly growing silicon carbide market, we have invested in the wafer fabs also with a lot of attention. So we currently have three running fabs of silicon carbide wafers. Two of them are in Chikugo, Japan. One of them is a 6-inch fab. The other is an 8-inch capable fab. The new building here. We also have a Miyazaki fab, which processed 6-inch wafers and started production of the fourth generation silicon carbide MOSFET from 2021. Recently, we acquired a facility, another factory in Miyazaki, and this factory will allow us to expand the production capacity more aggressively toward 2030. You can see with this added new facility, and starting production as early as 2024, we're looking at up to 35% times increase in production capacity in 2030 compared to 2021. This also includes our migration from 6-inch wafer to 8-inch wafer to improve the output capacity. ROHM's silicon carbide MOSFET has been used in multiple application areas. For example, communications, data centers, and renewable energy applications like UPS, solar inverters, of course, automotive vehicle electrification, and also industrial applications, including induction heater, battery tester, and motor drives. Okay, that's a brief overview of our silicon carbide business activities. So let's see what we offer with the fourth generation silicon carbide MOSFET technology. This is an overview of our silicon carbide MOSFET process evolution. We started with the second generation planar gate technology, and we started with 1200 volt and 650 volt class silicon carbide MOSFET. In the third generation, we developed a proprietary double trench gate technology, which allowed us to reduce the specific RDS(on) by 50%. This enables lower cost and also lower conduction loss. Similarly, with the new generation, the fourth generation, we cut the RDS(on) by another 40% and increased the voltage rating for the lower one from 650 volt to 750 volt. This is still using our double trench technology, and we further optimize the cell design and improve the process. So this enables one of the leading performing silicon carbide MOSFET in the market. Our current discrete lineup includes 750 volt and 1200 volt class with on resistance ranging from 13 milliohm to 65 for the 750 volt and 18 milliohm to 90 milliohm for the 1200 volt. Our gate to source voltage is rated at -4 volt to 21 volt DC and up to 23, including the surge gate voltage. Our main advantages for the fourth gen silicon carbide MOSFET includes the industry's lowest specific RDS(on) with the double trench MOSFET technology, lower power loss, including the switching loss that allows system downsizing opportunities. It is also user-friendly to support gate drive voltage with a flexible on-state voltage and no negative voltage required for turning off. With those benefits, we are not sacrificing ruggedness like short circuit capability. This is improving the trade-off between these two standards. With our current standard grade discrete devices, we offer on our website, you can see already three RDS(on) levels available for each voltage class. We are adding more resistance ratings to the lineup, so it can fit some applications with better products with less design margins and lower cost. So we have this range of discrete devices from through-hole type TO247 and surface mount type TO263. You can see this 4-lead and 7-lead packages. They offer Kelvin source connection, which helps the switching loss performance. And most of these products are also available as an automotive grade part, qualified under AEC Q101 test, and available for automotive design, especially onboard chargers or DC-DC converters. So those are the lineup of our first generation silicon carbide MOSFET. And let's see why you might want to use this new generation products and what packages we have available. The main benefit of this new generation of products, I could summarize in three areas. One is low loss, the other is easy to use, especially easy to drive, and high reliability. So why does the fourth generation silicon carbide MOSFET offer lower loss, especially compared to our third gen trench technology? So the first one is the reduced specific RDS(on), which means at the same chip size, we are reducing conduction loss and the RDS(on) by 40%. So conduction loss equals to I square R. You can see with a similar die size, you are really benefiting from lower heat generated from the conduction process. On the other hand, the switching process is also improved, especially the DVDT speed. Because of the lower RDS(on) and smaller chip size. It helps reduce the capacitance. And in addition, we have optimized the CRSS Miller capacitance, which allow us to reduce that value by up to 90% compared to the third generation similarly rated product. So the result of that is a much faster switching speed. You can see in the waveforms without even causing much higher surge voltage in the VDS. So with the reduction of conduction loss and switching loss, the fourth generation silicon carbide MOSFET offer a much better solution for most applications to design for higher efficiency power electronic systems. One of the example for the benefit of conduction loss reduction, we can see here. So we tested a buck converter using either a third gen silicon carbide MOSFET or a fourth gen product. So they are similarly, they're not the same RDS(on), but they are similar in die size. Uh, because of the lower specific RDS(on), we do improve the conduction loss by over 50%. That results in cooler operation temperature. You can see the thermal image we captured. That certainly will help the efficiency as well as the thermal management for the discrete products. Another example is to show the benefit of switching loss reduction. Let's say you are using a similarly rated Gen 3 and Gen 4 silicon carbide MOSFET around 40 milliohm. So the smaller die, first it will allow you to design the system with cheaper devices because the chip size is smaller. And also because you have a similar RDS(on), your conduction loss will be quite comparable. But on the other hand, the switching loss, due to smaller die size and also improved Miller capacitance, it switched much faster and resulting switching loss cut in half approximately, which enables higher switching frequencies. So the merit of the fourth generation switching characteristics is not just faster switching speed, but also to avoid a phenomena called self-turn-on, which could cause shoot-through current in a bridge circuit that adds switching loss to the circuit. You can see the capacitance characteristics of the fourth generation silicon carbide MOSFET compared to the third gen. The main difference would be the CRSS value. Oh, wait. So the CRSS value basically have a one order of magnitude lower value compared to the third gen. Not only this allow us to switch faster, but also the ratio between CRSS and CISS is much reduced. So with this improved ratio, when the device is switching and the drain to source voltage is changing rapidly, it influences the gate to source voltage by a less amount, which means there's less risk to turn on the gate accidentally during the fast switching process. With this reduced switching losses, high frequency switching can be achieved. And of course, this can lead to system downsizing by reducing the size of passive components with higher PWM frequency. So one of the example is shown here, the buck converter we tested, even at higher frequency, like up to 50 kilohertz, the fourth gen still is quite capable with good efficiency, while the third gen is dropping in the efficiency numbers. On the other hand, the reduced switching loss will produce less heat and make the heat sink volume smaller or the thermal management system simpler to make. So those are the comparison between our third gen and fourth gen silicon carbide MOSFET. So how do we compare with competitors? When we released the product, we actually did a benchmarking study with our 750 volt device compared to what's available on the market, which is usually 650 volt class. We compare the specific RDS(on) of our Gen 4 device versus 3 other main competitors. We can see at room temperature and 175 degrees C, we offer lower around times area. This same advantage can be shown at the 1200 volt class with 25 degrees C and 175 degrees C compared. You can see we have especially lower conduction loss at a lower temperature, with still leading conduction loss at higher temperature. Another benchmarking study is regarding the switching loss. We used a 30 milliohm part um, to compare our Gen 4 products versus three vendors. And we can see if we normalize the switching speed by allowing up to 80% of the rated current as the VDS surge, then we will have a lower conduction switching loss compared to the three other options in the range of 13% to 49%. So we offer lower turn-on loss especially. For the power conversion efficiency, you can see there are many applications like the PV inverters, EV charging stations, or any circuit that you will use a hard switching kind of switching control, then this switching loss benefit could be very evident. So in this case, we compared a buck converter with 100 kilohertz switching frequency, which is relatively high, and with the output power from 1 kilowatt to 5 kilowatt, this 40 milliohm class devices performed well, and they all exceeded 90%, 99% of efficiency when it is a higher power, but ROHM still have an advantage for all the power we tested. So we do have lower loss, and is the device easy to use? Especially, is it easy to drive? So I'll focus on what voltage we use to drive the fourth gen silicon carbide MOSFET and the internal gate resistance uh, implemented on the new die layout. So our recommended gate drive voltage for the fourth gen silicon carbide MOSFET is on state 15 to 18 volt. Why we can support this flexible range is because our RDS(on) dependence on the gate to source voltage is relatively flat in the fourth gen technology. Compared to the third gen, which actually we would not recommend a 15 volt drive because of the increase of RDS(on) is up to 30%, but this has been much lower for the fourth gen device. So if one of the application requires compatibility to a 15 volt drive, such as to be compatible with another vendor's product or IGBT design, then if the application really is dominated by switching process, or the conduction loss, or the minor difference in the conduction loss will not be a big contributor to the total efficiency penalty, then we could have the efficiency at 15 volt and 18 volt quite comparable. Of course, 18 volt will still give you slightly better efficiency because of the lower resistance for the on state and lower conduction loss. But 15 volt, if there's a need to drive at this voltage, we can support that. For turning off the device, we do not require a negative voltage. Many of our competitors do recommend or require a negative voltage to turn it off. One of the reasons is to avoid shoot-through current in a bridge circuit. So this is a pretty common phenomenon in power circuit. So when one of the switch in a bridge circuit turns on, it does introduce a high DVDT transient across the other MOSFET, which is supposed to be in the off state. But the VDS increase, uh, if it is very fast, then it could distribute the voltage between gate to drain and gate to source. And we don't want that voltage to appear on the gate to source terminal too much, because if the gate voltage exceed the threshold voltage, then this offset state MOSFET could be accidentally turned on. And when the two MOSFET are both turned on, then of course there's a shoot-through current that increase the losses. So how can we avoid this phenomena even without a negative off-state voltage? First one is we design our device with relatively high gate threshold voltage. Our minimum specification is 2.8 volt compared to less than 2 volt for some of our competitors using planar technology. The other is what I mentioned, the ratio is improved significantly between CRSS and CISS for the fourth gen silicon carbide MOSFET. And that ratio determines how much voltage you will see between the gate to source terminal. And that was minimized by this ratio. One of the example waveforms we can see here with fast switching speed, we still don't exceed the threshold voltage, minimum threshold voltage in the switching process. Another benefit for using the fourth generation silicon carbide MOSFET is reduced internal gate resistance. Compared to our previous generation, for example, one of the product we had a 7 ohm internal gate resistance, which means no matter how low external gate resistance you use, you will not be able to achieve a total resistance less than 7 ohm. For the fourth gen, we reduced that to about 1 ohm for many of the products. So this gives you more flexibility to design with suitable gate resistance on the external side, and that could improve the potential to switch the device faster. So with those benefits in low loss and gate drive flexibility, are we sacrificing any reliability or ruggedness factors? So the good news is we are not sacrificing, especially the short circuit withstand time. Normally, there's a trade-off between RDS on and short circuit withstand time. For example, from our Gen 2 to Gen 3, we did improve the RDS on by 50%, but we also sacrificed the short circuit withstand time quite a bit. But this is not the case when we introduced the fourth gen technology. With the reduced RDS on, we are maintaining or improving the short circuit withstand time because we use a unique structure on the chip to limit the short circuit current at high voltage. Comparing ourselves to other discrete products, we can see, so this test on the right, we turn off the device just before it would fail. So ROHM would have a longer short circuit withstand time, more than 5 microsecond, compared to less than 5 or even less than 2 microsecond from our competitors. A little more details of why there's an improvement. Normally, when we have the device evolution, if you improve for the on state, then at higher voltage, it will also increase in the saturation current. But in the design of fourth gen silicon carbide MOSFET, we actually improve the both sides. So low RDS on, but saturation current is suppressed. Okay, so those are the benefits we want to introduce for the fourth gen technology. So this slide shows our packaging lineup. At the lower end, lower power, we have discrete products and HS-DIP, which is a module for medium power, for example, onboard chargers. It is an integrated module with 4 or 6 devices inside. And on the medium, higher current between 100 amp to 200 amp, we offer a supersized through-hole package we call DOT247, which is about twice the size of TO247, but much higher capability to handle currents. This is also a half-bridge configuration. On the higher current side, such as for traction inverters, we offer power modules like the TRC drive pack, half-bridge module up to 600 amp rating, and we also offer industrial grade power modules like this traditional case type module. So this is just an overview of the new power modules, automotive grade power modules we have been developing for EV traction inverters, onboard chargers, electric compressors, fuel cell vehicle turbochargers. So we'll cover more details, especially on this traction drive module in our upcoming seminar in APEC conference in Long Beach, California. If you have opportunity to join us in APEC next month, I hope you can come to the seminar on this particular more details of this package, TRC drive pack. Okay, so those are all the device introductions I want to cover. We do also offer comprehensive application support for various applications, including automotive and industrial and power supplies. We offer support throughout the design cycle from specification to evaluation and mass production. We have simulation options, not only device models being available from our website, SPICE models or Plex models. We also offer a simulation right on the ROHM website called ROHM Solution Simulator, which include the common circuit topologies and a library of products for power design with power devices and gate drivers. We also have evaluation board available for power devices. You can do double pulse tests for our various packages with half bridge drive boards. Application notes are also available on the website. Please check it out. This is probably the last page about our thermal design. So in power circuit, usually not only electrical simulation is important, you most likely will need to do in-depth thermal analysis. We can assist in that. We can provide thermal models of our devices, perform thermal simulations according to the customer's PCB and module, and also even perform measurement and make proposals to make thermal improvements. Lastly, thank you for attending this seminar and why we should why ROHM should be your silicon carbide design choice. I think I will summarize in 3 ways. We are a technology leader in silicon carbide devices. We have fully integrated production from substrate to device and packages. And then we offer solutions beyond power devices, including gate drivers, IC product, and standard discrete. So you can have the same stop to shop for many of those components that you will need for your power stage design. Okay, that's all I want to cover today. So thank you.